All right, we're going to do a brief tutorial on Archimedes' principle and Bernoulli's principle, particularly some of the calculations, work through a few of those. So if we look at this on Archimedes' principle, remember Archimedes talks about the weight of the water displaced being equal to the buoyant force acting on it. So if it's floating, that would also equal the weight of the boat in this case, since it's floating. So let's look at the calculations. So for part A, we will know the mass of the water displaced by the boat. Since it's water, we're talking about 1,000 kilograms per cubic meter. And the volume of the boat that is submerged, that thereby displacing water, is 4 cubic meters. So density equals mass divided by volume. So we know the volume and we know the density. So what we're solving for is the mass of water. So mass is equal to density times volume. So that's going to be 1,000 kilograms per meter cubed times 4.0 meters cubed, which will give us, after the meters cancel, 4,000 kilograms. And so that would be your answer to part A. Part B says, what's the weight? Remember, weight is equal to mass times the gravitational constant. So we're going to use our answer from part A, 4,000 kilograms. And then we're going to multiply by the gravitational constant. We'll use our rounded off value of 10 meters per second squared. So 10 times 4,000 is 40,000 newtons. So that's your answer to B. That's the weight of the boat. Now, as I was mentioned before, since the boat is floating on the water, then the buoyant force must be equal to the weight of the boat, or it wouldn't be floating. So guess what? The buoyant force, B-U-O-Y-A-N-T, force, is equal to the 40,000 newtons. And so the weight of the boat is also, for part D, is also 40,000 newtons because the boat is again floating. Okay, so that is Archimedes' principle. Look at Bernoulli. So now we're talking about flow rate of a fluid. In this case, the area over which it is flowing is less, and so ideally it should speed up because the volume of flow should be the same. That is, if I've got a fat pipe and it narrows, you've got a linear velocity v, but it's going to be bigger in the narrower section because you've got a bigger cross-sectional area versus a smaller cross-sectional area, and the volume of fluid flowing through each, that is the flow rate of each, needs to be the same. And so the linear flow of the fluid needs to increase to keep the flow rate in terms of volume to be the same. So really the flow rate's related to the area, but for a circle, that area is pi r squared. That is the cross-sectional area of the pipe here and here would be given by the area of a circle. And so really we can interrelate. If the area gets smaller, the velocity should get faster. So there is an inverse relationship between the two. So essentially we say linear velocity times area for the first section of the pipe equals linear velocity 2 versus the area for the second cross section of the pipe. We'll make this 2, we'll make these 1. We plug in our area, what we find is that we got pi r squared for the first section, and then pi r squared for the second section. Pi is a constant and it cancels. So what we get is v1 r1 squared equals v2 r2 squared. And then it's just a matter of plug and chug. So then we can solve for the speed in the narrow part. We know it. In the wide part, we need it in the narrow part. So v2 equals v1 r1 squared over r2 squared. So 2 meters per second times 6 centimeters divided by 4.5 centimeters. Centimeters cancel. And so I get away without converting these are squared. You get away without converting the lengths because this is a proportion and the centimeters will cancel and you'll get the exact same answer. So 2 times 6 squared divided by 4.5 squared is about 3.6, we'll say, meters per second. So the linear speed of the fluid flowing through the pipe is 3.6 meters per second. But this has been a brief tutorial on Bernoulli's principle and Archimedes' principle and the calculations in this chapter.